Thanks, everyone. So I'm going to talk about this work called Noise2Self, Blind Denoising by Self-Supervision. And I know it's late in the day, so there will be at most one idea in this talk, and it won't be that hard. But hopefully you'll find it to be somewhat useful. All this work is joint with Loic Royer, also at the BioHub, and there's a link to our paper there, which will be, Google that if you want it. So I want to start with these three images. I'm doing the thing where, like, discovery goes in one way, and then you completely reverse engineer it. So this is just from 2 weeks ago. I was looking at my colleague Anita's computer at these three frames, and she was looking kind of dejected. And the reason was that she was trying to train a machine learning model to predict the middle one. It's a fluorescent stain on, these are kidney slices actually, from the thing on the left, which is birefringence. The idea is you don't need to do any tagging there. You can just take it with a regular light microscope. So thing in the middle, expensive to acquire, thing on the left, cheap. If you can predict the expensive from the cheap, then you're happy, and you can do more imaging at less cost. And so if that's X, that's Y, you train a model to get this. And what she was upset by was that the accuracy of the model was like peaking at 80% with the thing on the right. That's the prediction. I came by and I was like, oh, no, this is great news because the thing on the right is better than the thing you were trying to predict. Okay? Like, it's very smooth. It's getting the structure you were labeling, and everything it's missing, these like vagaries of where the stain hit, is like not really what you're interested in. Right? So you can think of this as being learning from noisy labels, where the stain is like a noisy label for what you want. And then if you train a model to predict it, what comes out, won't be able to capture the noise, but what comes out might be better than actually what you were aiming for downstream tasks. And so the reason we were thinking about this is just oh wait, I'm spacing out. So theorem, I guess, proposition. So how does learning from noisy labels work? So you have three things. You've got X and Y. X you predict Y. Z is the truth. If the noise is conditionally independent, right? So if I tell you the truth, and then I tell you the input doesn't help you guess the way it's noisy, and then also if the noise is mean 0, then your objective function, so f of x minus y squared, which is sort of noisy loss, is the same as the ground truth loss, f of x minus z squared, plus the variance of the noise. And this is just, there's a cross term here. This is true for any function. The cross term vanishes because of this independence. And so if you wanted to optimize, there's no laser. If you wanted to optimize this, like with clean training data, what's behind the computer?
The laser.
Oh, the lasers. Great. I've got two things now. All right. So if you wanted to optimize this, but you just had noisy labels, that's fine. You can just optimize that, and this term is independent of f. So everything sort of goes great. And the reason this is important, I think, in sort of all of science is that all your data is noisy. This is the noisiest data I've ever seen. Does anyone recognize what this is? Yeah. It's like a single protein. It's like one molecule in a cryo-EM scope that you destroy it when you hit it with electrons. So your signal-noise ratio is 1 to 10 because if you keep imaging, you're imaging garbage. But they get so much of it. They get hundreds of thousands of things which are very bad. On the right is some super resolution data, but the data is sort of noisy in general. And so there was an idea for denoising that I saw about a year ago at ICML called Noise2Noise, which is just an application of this noisy label thing, where if you have one noisy measurement of the object and then you have another noisy measurement of the same object, you can treat the second measurement as a label for the first one. So just try to train a neural network to predict a second noisy measurement from the first, and well, you'll learn to do the right thing because you can't guess the noise. And so if you train something there, you get what you want. And this is just from their paper. They show that the actual full training curve with clean targets and noisy targets is the same, right? And this is great. So if somehow you can get yourself in a situation where you can take independent noisy measurements of the same thing, then you're set. You could just train something like this. And it'll work. But that can be difficult. For example, if you destroy the thing you're imaging when you measure it, or if the thing's very far away and so you're getting very few photons from it or something. OK, so this is a meme. Basics, yeah, undergraduate, little brain is what if all your data was clean, right? So you could fit your PDE salt, that can be great. But that's not really the situation. But maybe you could do something expensive and acquire clean labels somehow, right? And then you could train on those and then go to your noisy regime and apply what you learned. Noise to noise is like your labels could be noisy, right? And you would also be all right. And then the idea is like, what if you are your own label? All right, that's like the crackpot idea. And it's a bad idea, right? Because like, you know, what is argmin of f of x? If x is your label, what's argmin of f of x minus x squared? Yeah, the identity function, and you get 0 loss. Like, congratulations. Like, and so that's okay. So there's like autoencoders can work, denoising autoencoders, where you somehow cripple f. You work with a restricted class of functions f, some kind of a bottleneck, and then you hope that it's unable to learn the noise, so it can't pass the noise forward. But this is a little odd because like now you're in this business where you try to make a class of functions which is bad, but like good enough to learn the signal, but like not so good that it can pass the noise through. And so you're kind of turning this crank, and you don't really know where to put it. Okay. So the idea here is sort of twist on that, which is just a kind of self-supervision. So the basic idea is that real clean signals have a lot of redundancy in them. Okay, there's a lot of extra information. So here's a face, and if I cover up these pixels here, these red ones, calling some subset J, you can guess what goes there, right? Like the ones on the head should be black, and the ones on the upper right should be gray. You could totally fill it in. There's a lot of redundancy in this high-dimensional space. You could guess what goes there. If what you have is something noisy, and you cut those out, well then if you believe that like you could do inference if you knew like a prior on the way images look and you knew the noise model, there's some function given training, right, which could take you from here to here. This could be explicit, right, like Bayesian inference. It could be that you just train something from data. Double fisting again, okay. And the basic idea is that if we instead predict these pixels from this, and we have some independence assumption about the noise, then again, this is just a noisy label for these. And so you'll actually learn to fill the missing ones in. So that's great, because this is a single noisy image. You do this thing where you sort of mutually pull parts of it out and use those to supervise the learning. And then you just go back through and you replace absolutely everything in your data with the prediction from the rest of it. And if there's a lot of structure, your prediction from the rest is better than any one value for the pixel. So a definition, maybe it's too short of a talk of a definition, but anyway, the idea is, what's the class of functions we're going to use? It's functions where we've partitioned our feature dimensions into a bunch of subsets such that the output of your function in some features J doesn't depend on the value of the input there. I mean, so for pixels, this would be like you can use anything you want to predict this pixel except the input in that pixel. And if you have such a class of functions, and the noise itself satisfies some conditional independence and is mean 0, now f is J invariant, then this thing isn't going to be 0, right? The identity function is the opposite of this. The identity function uses a pixel to predict itself. This uses everything else. And so you get this self-supervised loss here will just be numerically equal for all functions to the ground truth loss, which you wanted to minimize, plus a constant that doesn't depend on f. So if you optimize the self-supervised loss among such functions, it's the same as optimizing the ground truth loss. So let me give you a, we're at 6 minutes, great, okay. So a very like low-key, no neural net basic example. Doughnut median is what we're calling it. And so you have ground truth, you have the noisy data, and you're going to look at median filters, right? You just pick some little window, you replace each pixel with the median of things in that window. So if the window's really big, you'll get a blurry image, but with little noise. If the window's very small, you'll keep some noise. And so the question is, like, where in here should you stop? Like, which of these is going to be the closest to the ground truth? And in the situation where you have no access to the ground truth. OK, so if the sort of classic thing to do would be like using the whole input data to take your median. That's this little thing here. And in, you know, OK, it gets worse. Sorry, it gets better, and then it gets worse. The optimum's at 3. If we look at f of x minus x, which is the solid orange line, it's completely uninformative. right? Because the identity function is the best thing to do. Don't do anything would sort of be over here. But if we instead use a slightly modified version where you don't use the middle pixel, then you get the solid blue curve where things get better and then they get worse. And from the equality from the previous thing, it says that the dashed blue line, the ground truth loss, and the solid blue line differ by a constant, which is the noise variance, which is independent of f. And so if you wanted to know the best hyperparameter to use for the donut median, you would find it here, directly under the minimum of the self-supervised loss. And that's good news because you can compute the self-supervised loss from noisy data. And so this lets you optimally calibrate this donut filter from the noisy data you started with. OK, this is a simple example. Like maybe medians aren't the thing. Medians are some sort of smoothness bias. Maybe you're coming in with a different prior. Maybe it's like a wavelet prior, so you think things are sparse in some basis. Maybe your prior is like a patch-based prior, like self-similarity. And if you can just modify that by a little twist so that it becomes invariant, then you can do the same thing. So you could calibrate any of these classical models in the same way, where again, we just have access to the blue or solid orange things. But because it's the same as the dashed lines up to a constant, we can see that actually for this image, non-local means is the best prior to use. And it also indeed performs best on the ground truth data. And so you can sort of find hyperparameters through one method and also choose between methods. This was made possible by having scikit-image, making it really easy for me to like swap in different methods to try. Thank you, Stefan and crew. There's a PR in to try to put this in scikit-image if you want to review it. Open source, baby. All right. So I think I'm, OK. We're close to time. Let's just say that one image is actually a lot of information, right? I mean, the astronomers are like, we have way too much information. But even one image is a lot. There's 250,000 pixels. And so a neural net like might have 100,000, a million, 2 million parameters. Not that many compared to the data in one image. So if you can do self-supervision, then you don't need very many images before you have enough data to learn a lot. So we could train like a UDent or something to denoise a single noisy image, and it works. So you don't just have to calibrate. You can train with self-supervision and get what you want. Of course, if you have more data, you can do better. So this is a sort of final example. First, see how your like in-brain neural net does. OK, does anyone recognize what these are? OK, they're Chinese characters. And if you speak Chinese, you might recognize their actual identities. If you don't, it might be a little bit tricky. I think no one has recognized all of them, even with good prior of being fluent. But you can train with self-supervision, and it becomes a lot clearer. And so one advantage of this is that you don't have to come in and do inference with a prior you had. You also don't have the usual problem of supervised training, where if you're out of sample, right, you train on something and then you go on something else, you'll end up hallucinating your training data into your observations. So then the final thing to close with is you can also, the stuff in the paper, last shout out, you can do this on astronomy data, where think of it as how do you reduce uncertainty, and don't average train. Okay, so don't use averaging of the pixels you have, but maybe you can train something and do better. And this is ongoing work with Brian in the audience. And with that, I'll close. Thank you.